Okay, guys, so I think we are good to go. So hey, hi, formally, good evening to all. So as you know that we are doing this series of workshops. First, we have started with these partner-led workshops. Today, it's Neo4j workshop, and we have two amazing folks with us, Martin and Akmal from the Neo4j team. And it's so nice to see you guys. Hi. So
Thank you very much for having us.
thank you. It's a pleasure. We are grateful for to Neo4j for supporting this hackathon. So as you know that we have a Neo4j AuraDB track as well. So teams building on Neo4j AuraDB are of course eligible for bonus points. And I hope this workshop is fruitful for everyone. So without further ado, over to you guys, all yours. Thank you.
Thank you so much. So just give me 1 second. I'm just going to put all of these windows in the right place. So if I'm looking this way, I'm looking at you guys, right? If I'm looking this way, I'm looking at my slides and what's going on and things like that. Okay, so let me just share my screen. So screen, we share this one. So yes, thank you for the introduction. So what we're going to do today is we are going to do sorry, okay, right, it's fine. I'm just making sure I can see everything. So we're going to do a Neo4j and generative AI workshop. So we're going to learn how Neo4j and GraphRAG can support your GenAI projects. So just a couple of things. So first of all, thank you for the introduction. My name is Martin O'Hanlon. I work for Neo4j in developer relations. A lot of my work at Neo4j is creating educational content and delivering workshops like this one. So just a little bit of sort of etiquette, like please mute your microphone, otherwise we'll have to mute you, just because it can get quite distracting, and we are quite a big group, so sort of 55-ish people. Please ask questions in the comments. Akmal is here, and we'll try and respond to any questions. Please ask for help. Like just a sort of a point of note, this is a hands-on practical workshop. Like we'll probably be unable to deal with individuals' issues, but again, please ask for help in the comments as well. That would be super helpful. All right, so meet the team. We've got myself, Martin, Akmal helping with comments. You can find us both online. We are both pretty easy to find, both as Martin O'Hanlon and obviously Akmal Chowdhury. Okay, so without further ado, this is what we are going to do today. So I'm going to break this down into 4 things. We're going to talk about what is generative AI and how Neo4j can help you improve your GenAI applications. We're going to do, and then we'll move on to do some knowledge graph construction. So we're going to create a knowledge graph using unstructured data. Third, what we're going to do is we're going to build some retrievers. So we're going to connect your knowledge graph up to do GenAI retrieval and create some sort of simple question response patterns. And then finally, if you want to, there is a section which continues on from the work you will do today to look at how you can build those retrievers into an agent. All right. So the first thing that I'm going to introduce is I'm going to introduce Graph Academy. So Graph Academy is Neo4j's online training platform. We are going to use Graph Academy today as a way of giving you access to all of the content that we're going to go through, but also giving you access to a Neo4j database that you can use as part of this hands-on workshop. Okay, so that's Graph Academy. In addition to this one workshop, you will also find lots of online courses where you can learn more about Neo4j and about generative AI, how to mix those two together, or some of the other tools and some of the other fantastic capabilities that Neo4j gives you. All right, so what do you need? So you are going to need 2 things. You are going to need a Graph Academy account, which you can get at graphacademy.neo4j.com, and you're going to need access to the workshop content. Now, I have put all of the links and everything that you're going to need in a document here. So if you go to dev.neo4j.com/workshop-generative AI notes, it will take you to a document that looks like this. So what I'll do is I'll post this link in the chat. And this document has got everything in it that you need. So it's got a link to Graph Academy. It's got a link to the workshop, and it's also got an OpenAI key that we're going to use later on in this workshop as well. So your first task is to head over to dev.neo4j.com/workshop-GenAI notes. Again, I've pasted that link into the chat. Once you've got there, go ahead and sign up to Graph Academy, and finally go to the link below, which will take you to that GenAI workshop. So I'm just going to put a note in the chat saying all the links you need. Sign Graph Academy and go to the workshop. Content. Okay, yeah, so that link's going to stay there in the chat, so you can come back to it if you need. In fact, I can pin it. Oh. Yeah, let's pin this message. Okay, yeah, so first job, go to this link and sign up for Graph Academy. When you get to Graph Academy, you're going to see a window that looks like this. In fact, I will just sign out, and you can sign in here. You can either create an account, or you can sign in with Google or GitHub or something else that makes sense to you. I will sign in with Google. So this is going to take you to Graph Academy, and then we're going to use this second link, this link here. So this workshop, the workshop that we're going to do today, is not public, so you will need to follow this link. And once you follow this link, you're going to end up at this workshop, which is the Neo4j and Generative AI workshop. So I will give you a minute just to do that. I will also paste the links into the chat as well. There we go. We've got a little thumbs up. I'm guessing that means people have been successful in signing up for Graph Academy, which is great. Okay. Yeah, so this is this notes document. Keep an eye on that, and we'll come back to this in a little bit to get this API key. All right. So you should be here. You'll have a little button that says enroll to the course. Please do that. And once you do, you're going to end up here. So this is Graph Academy. This is the content that we are going to go through. Here's the little menu that sort of shows you where you are and how to navigate around the course. And you can see those 4 modules that I spoke about. You know, one about generative AI, one about knowledge graph, one about retrieval, and one about agents. So what I'm going to do is, I'm sure people are still signing up. That's fine. I'm going to kind of like kick off and just talk through some of the introduction. So this is Graph Academy, right? Once you've signed up for the workshop, you are going to see exactly the same content that I see and I present. I have a mode here, which is a slide view mode. This allows me to present slides rather than the text. But again, you see exactly the same content that I see, and that's a sort of theme of how we're going to deliver this workshop. I'm going to present. You can see the same content. You can do exactly the same activities that I do. All right. So what we're going to do is we're going to spend a few minutes just talking about what is generative AI and defining some terms and making sure that when we talk about certain things, so when we talk about models and when we talk about LLMs, that we all are talking about the same thing. Get us all on the same kind of footing, talking the same language, and then we can use these techniques to create our knowledge graph. All right. So when I talk about Gen AI, I mean generative AI. I tend to shorten generative AI. And what I'm talking about is artificial intelligence systems that create new content based on training data. So Gen AI models, you know, your GPTs, your Geminis, your Claudes, your insert name of model that you like, right? They all work in roughly the same way, which is they take huge amounts of training data, whether that's pictures, images, audio, video, whatever, create a model based on that data, which allows them to create new content, ultimately based on that training data. And that new content is designed to resemble human-made data. Let's, cover off the things that hopefully we know. Gen AI models, they're not intelligent in the way that humans are. They do not understand or comprehend the content that they generate, and they rely almost entirely on statistical patterns and correlations. So while they can produce coherent and textual outputs, they lack understanding, and that creates challenges for us. So the workshop that we're going to do, we're going to focus specifically on text generating models, specifically large language models. And again, your Claudes, your Geminis are predominantly large language models. And LLMs, or large language models, work almost entirely in the same way, which is the note, the definition I've given here is a probabilistic continuation of the instruction it receives. And the words here are the words that are important here are probabilistic, continuation, and instructions. So when presented with an instruction, its job is to say, what, based on my training data, will probably come next. So if I give it, continue the sequence ABC, an LLM could respond with DEF. That would be a probabilistic continuation of the instruction it received. And the way that we get an LLM to perform a task is we give it a prompt. That is the instruction that we give it. And prompts can be simple, or they can be very large, but they should always specify what you want to happen and give clear instructions. Let's just talk about some caution. Huge amounts of potential, but they are at their core highly complex predictive text machines. They do not understand, and they cannot also tell you how they generated that information. The other thing is access to data. So LLMs, Gen AI models, almost entirely trained on publicly available information. And it's huge amounts of information that could be of questionable quality. And it also happens at a point in time. The data is static. Once the model is released, its training data never changes. So it may not reflect the current world. So, when we ask it, tell me about the latest Neo4j features, unless it's given any additional information, just based on its training data, here are some old features with incomplete information. Again, accuracy. They're to generate to design human-like text and tuned to be as helpful as possible. So they can present information which is presented as fact, but is completely untrue. And, we call that a hallucination for those reasons. It is believed to be true, it is presented as true, but it's completely made up. But we can improve the accuracy of responses from LLMs by providing context. So if we provide context around relevant information towards the task that we want it to do, we get a better response. So let's look at this use case. We provide a prompt that says, summarize a company's results, right? And the LLM, based on its training data, could return us back some information. If, however, we provide a stock market report alongside our prompt, so we provide it with additional information, we will get a better response from that LLM. Access to data, as we've said, fixed knowledge cutoff. The more information the more specific the information we provide within our prompt as context, the better the response that we get. All right. So the point I want to leave us with here is supplying context in your prompts helps LLMs generate accurate, relevant, trustworthy responses, reducing hallucinations and compensating for the lack of access to data. That is, in a statement, what we are going to do today is look at how we can provide our LLM or a generative AI model with the best context that we can in order to solve the question or the problem or the challenge that we have presented within our prompt. All right. Okay, cool. So that's me talking for a little bit. So what we're going to do is we're going to go on to the next one. So we're just going to talk about GraphRAG for a bit. All right. So RAG, or retrieval augmented generation, is an approach that enhances the responsive LLMs by providing them with relevant, up-to-date information. RAG is a mechanism for giving context or working out the context that we need to be able to give to get a better response from our LLM. And typically, the RAG process looks like this. We have a user who gives a question to an application. The application will use a retriever to find additional context, and it gives that additional context as an enhanced prompt. So it takes the prompt from the user, adds the context to it, gives that to the LLM to get a better response, right? And that is the kind of the traditional RAG process. So, you know, if we were looking at, okay, well, what we want to do is we want to build a chatbot around giving us the latest information on the Olympics. Information on the Olympics is going to be real time. It's not going to be based in any LLM's training data. But what we could do is build a newsbot chatbot that pulls real-time data, supplements its real-time data, supplements the prompt with real-time data to get a better response. The retriever is the key component within the RAG process. The retriever's job is to search for relevant information that is appropriate to the question that it's been given. So typically, a retriever takes some unstructured input, like a question or a prompt, and it searches for structured data that it can use to provide context. And Neo4j provides kind of various methods for doing this, and we will explore those as part of this workshop, and we're going to build them as part of those workshops. Now, in order to provide our LLM with good context, we need some data sources, and they can be documents, APIs, knowledge graphs. It doesn't really matter what they are. The retriever's job is to look at those data sources and be able to find the right information, but just enough information as well. So let's, expand our news chatbot use case. So we've still got our news chatbot. We've still got an LLM that's based on some training data. What we can do is we can provide a knowledge graph that sits in between our chatbot and our LLM. And that knowledge graph can be built from articles or an API or documents or structured information or whatever else we think is the right thing in order to be able to get our data out. All right. Now, so that's RAG. So GraphRAG is an approach that strengthens RAG using a graph database. Now, GraphRAG was a term that was coined by Microsoft as part of a research paper they did. I'm guessing 2024-ish, maybe earlier than that. And that original paper set out this approach, which is that you can improve vector search by enhancing it with a graph. And the typical process looks a little bit like this, which is a user asks a question. The application uses a vector index to find similar information. It then uses a graph to find related information about the sort of unstructured data that it's found, and it can then use that as a prompt. And the kind of results of this research basically said you get richer context, improved accuracy, explainability, flexible queries, and enhanced reasoning. So there was good reasons for doing it, and we are going to explore that today. Simran, please explain more about GraphRAG. I will. What I'm going to get you to do is actually get you to build a GraphRAG retriever. What I'm doing now is just sort of explaining the terms. Yeah, absolutely will. In conjunction to like the GraphRAG, we can also use full text search, and we can also use text decipher. So text decipher is a way of turning a question into a query that we can use as part of our retrievers. So we provide a natural language question, and then use Cypher to query our graph. It's great that you're putting questions in. Please put them in. What I will do is there are points within this workshop where you are going to be doing things, and I'll take that opportunity to field some of the questions at that point as well. Okay, so this is GraphRAG. Finally, I'm just going to the last bit of me talking is just talk about knowledge graphs. So I have used the term knowledge graph, in the last sort of five minutes while I've been talking. I just want to give a definition and give an example of what a knowledge graph is, because we are going to be talking about them. A knowledge graph is an organized representation of real-world entities and their relationships, right? So knowledge graphs provide us with a way of representing things, entities, their attributes, information about things, and how those things relate to each other, right? And it is an incredibly flexible structure that allows us to show how data and information is interconnected, right? And knowledge graphs are incredibly useful for generative AI applications. They're structured, and it's a very structured format, but it's incredibly flexible as well. And that's why it's helpful for generative AI applications. So search engines typically use knowledge graphs to provide information about people, places, and things. Knowledge graphs are not new things. And this is a knowledge graph that I created about Neo4j. It describes how Neo4j, the company, is related to Neo4j, the technology. The fact that Neo4j was founded in and is located in Malmö, which is a city in the south of Sweden. It's also located in London, so on and so forth. But it describes things and how things are related to each other. All right. Knowledge graphs are also really helpful because we can use this structure to break down sources of information and integrate them. So if we have sources of information, we can describe where those sources came from, and also information about those those sources. Graphs in Neo4j are schemaless by default, which means that they are very easy to change and adapt and evolve, because knowledge graphs grow quite quickly. Again, we can use this flexible structure to describe how our data, how to categorize and describe our data. So, for example, if I look at Graph Academy, right? Graph Academy has lots of different types of content, including lessons, videos, challenges, quizzes, so on and so forth, right? Yeah, and like I say, inherently flexible. And the great thing about a graph in terms of this flexible structure is that we can store the categorization of our data, or our organizing principles, alongside the actual data itself as well. All right. So GenAI applications, knowledge graphs play a crucial role by capturing and organizing important domain-specific information, so like the information that describes what, but they are not limited by structured data. They can also integrate how to represent information, and how and incorporating unstructured data as well. All right, so this is enough of me talking. All right, so we are going to go on to set up a development environment, right? So this will be a hands-on workshop from now going forward. I have done all the talking that I want to do in terms of describing terms. So what we're going to do now is we're going to set ourselves up a development environment. Now, Neo4j has a GraphRAG for Python package that allows you to access Neo4j's GenAI functions, and we are going to use that today. Now, there is a repository that we have created. It's at GitHub, Neo4j Graph Academy /workshop GenAI, and it's got all of the starter code and information that you will need in order to be able to complete the activities in this workshop. Now, if you've never used GitHub Codespaces before, I would recommend that you do. So what a GitHub Codespace allows us to do is to create an IDE in the cloud. So you don't need to install anything. You don't need to install VS Code or Python or even the Neo4j GraphRAG package. So I would encourage you to use that. So we are on this lesson here. We're still in this first module. We're on GraphRAG for Python, and we're going to open up this repository, and I'm going to use the GitHub Codespace. When I do, it's going to fire into GitHub. You only need a GitHub account. This isn't going to cost you anything. There's this scary note that says Codespace usage paid for by me. You're giving someone like 120 hours a month. We're not going to use anything like that. So and you're not going to get charged unless you say you want to. So we're going to create this code space, and what this is going to do is it's going to clone that repository that I've created for you that's got all of the startup code, and it's going to install everything that you need in order to be able to do this workshop. All right, so I'm going to do the same process as well. So I've just kind of kicked this off. It takes a minute or so to kind of like clone the repository, open the remote environment, and install everything. So yeah, ask that you do this do this yourself. So we are on this lesson here, GraphRAG for Python. All of the instructions here. Like I say, I would recommend you open it up in a GitHub Codespace. If you do want to develop on your local machine, or for some reason you can't use a Codespace, there are instructions here to do that as well. And once you've done that, you need to set up your environment. So set up your environment. Once my Codespace is opened, I will go through the same process as well and set up my environment. But yeah, all of the information you need is here. And while you are doing that, I will just have a quick look through the use cases. Sorry, not use cases, the questions that we've had. I'm just going to go from the bottom up. Can you ping me the link for the repo? Vijay, the repo is in the Graph Academy course content. All of the links that you need are in this document here. Again, oh yeah, somebody's already done it, but yeah, all of the links are in there as well. Okay. I'll just have a quick look through some of the other questions. Gory has a question. What are the major use cases for GraphRAG? So I mean, they're wide and varied, right? And a lot of these questions, that's a very open question. It depends. But the major use case of why you would use GraphRAG over RAG is predominantly is if you have strong requirement for accurate information. So if we compare RAG and GraphRAG, and I'm talking about vector-based RAG versus GraphRAG, vector-based RAG, if you've got vague queries, right, and you're looking to pull back similar information, yeah, vectors work great, right? But however, if you're looking to ask questions like, tell me how many, what was the outcome of, yeah, whereby a similarity search may not bring back the information you need. That's where using a graph to supplement that information with facts and information can be incredibly helpful. So major use cases we know, things like customer engagement, fraud detection, recommendation, things like that. Yeah. Okay, so I'm just going to nip back and see where I am. Right. Okay. So what is I'm back on my code space. So this is what you're going to end up with. Let me just zoom in a little bit. So this is the code space that you can use. And as you've kind of seen, what it's done is it's cloned that repository that's got all of the starter code in it. And it's actually gone through and installed everything that I'm going to need in order to be able to do this workshop. So this is, and I'm just going to preface this, the hardest bit of this workshop. We're going to set up our environment. So once you've cloned the repository, we need to create an environment file. So this environment file here contains the information which is relevant to the Neo4j instance that it belongs to you. So when you enrolled in this course, Graph Academy created a Neo4j database for you to use. So we're going to need this information. So I'm going to do the same. What I'm going to do is I'm going to create a new file called .env, and I'm going to copy the information from there into here. Now, this has got your Neo4j database connection, but what you're going to need is an OpenAI API key. And if you go to the document that I shared earlier, you'll see it's in here. Here is our OpenAI API key. We're going to need that because we're going to use OpenAI's embedding models and LLMs to complete the workshop. So I'm going to need that. I'm going to pop that in there. It's a very, very long number. So now I've got 5 things, right? I've got my OpenAI key and I've got my connection to my connection details for my Neo4j database. Like I say, don't copy mine, right? Yours are here. When you enrolled in Graph Academy, it created a brand new database for you. But once I've created my environment file, again, there's instructions here to test the setup, and you can test the setup by running this program, testenvironment.py, which is what I'm going to do. And if you have everything set up, what you should see is it's going to run 5 tests. We should see an OK message. There we go. What it's done is it's connected to that Neo4j database. It's connected to OpenAI. It's basically made sure that everything's set up right. If, for example, you forget to put the OpenAI key in and you put in one that's wrong, if I run the program again, you're going to see a fail because it OpenAI connection failed. The other one that people do is that sometimes they get the name of this file wrong. So maybe we left off the dot and just called it env. And if we run the test environment again, we're going to see .env file cannot be found. But yeah, so your job, and I'll be great to see some thumbs up, is to create this environment file, to set up your environment, and be able to run this test environment. Look at that, thumbs up. Lovely work. Yeah, and they're from different people as well, which is also good, right? Yeah, and run those tests. If you have questions, please put them in the comments. It's really difficult for me to kind of come back just because there's so many people on the... oh, look at this. All sorts of people going through, right? Okay, right. So yeah, just to okay, lots of thumbs up. I'm going to continue, but we are. If you want to set up your environment, we're in this GraphRAG for Python lesson here, and what we're going to do is we're going to use this environment throughout the workshop to create our knowledge graphs, run retrievers, so on and so forth. All right, so let's move on to this next module, which is all about creating a knowledge graph. So what we're going to do is we're going to create a knowledge graph using that GraphRAG for Python package, using some unstructured data. So let's have a think about how we're going to do this. So what we're going to do is we're going to take some unstructured data, so text, yeah, and we're going to construct a knowledge graph using that text. So in order to do this, we're typically going to follow 5 steps, right? So if we want to create a knowledge graph from some sort of unstructured text data, the things we need to do is we need to gather that data. We need to chunk it into bits, because quite often it's going to be quite, if it's a 148-page document, we need to chunk it into smaller bits somehow. We might choose to vectorize it, so to create embeddings for it, and we'll talk about vectors and embeddings. And we will then pass that data, that data to an LLM and say, can you extract the nodes, the things, from that text and the relationships as well? And then we then use that output to generate our graph, to generate our knowledge graph. So that's the process, five-step process: gather, chunk, vector, extract, and then generate. Those are the things that we're going to do. So if we were going to walk through an example, if we wanted to create a knowledge graph based on the Neo4j Wikipedia page, we would, gather the text. So Neo4j is a graph database management system developed by Neo4j Incorporated. Chunk that text in, split that text into chunks, generate embeddings and vectors for each one of those chunks, and then extract the entities and relationships using an LLM. So we would pass the text for each blob to an LLM with a prompt saying, your task is to identify the entities and relationships, and they would then parse those entities and relationships. So based on what we would get back, we would then use that information, use the entities and relationships that came back from the LLM to generate a graph. So going right back to our Wikipedia page, we would end up with a graph that said Neo4j, the graph database, was developed by Neo4j Incorporated, the company, and Neo4j graph database is implemented in Java, which is a programming language. We have extracted those facts, that information from our unstructured data, put it in a graph that we can query and form part of our context for our applications. All right. So that's the process. So let's start off by doing this. So we're going to go to the second lesson in this knowledge graph construction. And what we're going to do is we're going to look and see how can we extract a schema from text. All right. So this GraphRAG for Python package allows us access to these GenAI functions. We're going to use this package to build that knowledge graph. But we're going to start with how do we extract data from text. All right, so this is your job. If you have created your dev environment, maybe if you've used a code space, you've got a job to do. So in this part, you can continue. You can follow the instructions yourself. But if we open up this file, so workshop GenAI extract schema, workshop GenAI extract schema. This is this little program. And what it's going to do is it's going to create a prompt instructing the LLM, pass that prompt and text to the LLM for processing, and then parse the JSON response. All right. So you can all do this. Run this program. So this is this program. We can see that it's creating the schema from text extractor. We can see the text that we want to create a graph from. And if we're and we can also see the model it's using. In this case, it's an OpenAI model. But if we run it, this is the text that we're going to pass in. And we're going to do entity and relationship extraction on that text. And we're going to end up with this information that's going to describe the nodes, the relationships. So a graph database, a company, was developed by the graph database management system, was developed by the company. Oh, here, and here we go, it's returned. So I ran the program. We can see the node types, including a company. I'm just sort of scanning through. We can see the relationship types and we can see the patterns. Oh, I've lost my slides. Where have they gone? Oh, they're here. Right. And ultimately, what we can do with that information that we have extracted is we can build a graph. All right. So have a go, run that program yourself, that extract schema program yourself. Also, to experiment with some different text inputs just to see what difference it makes. I will take a little bit of a quick look at the questions and just see what people are saying. Akmal, thank you for responding as well. Katika, voice is breaking. Is anybody else having problems hearing me? If I can get a thumbs down, maybe, if people are having problems.
Martin, this is Akmal. I can hear you crystal clear. No problems at all.
Okay,
so,
all right. Okay,
it could just be temporary kind of internet connections globally.
Let's hope so. So. Okay. Hector, we've got some questions about use cases. I've been comparing knowledge graphs with vector database and RAG systems, understanding that graphs are stronger for structured semantic relationships, or vector systems are stronger for similarity-based retrieval and generation. I mean, I don't disagree with that statement, Hector. I think one of the things that we can see is that we can use both. In fact, Raj goes, I'd go with a hybrid approach. I'd keep a knowledge graph as a core, perhaps I can, and then add vector database with RAG on top. Yeah, and we can use Neo4j as a vector database as well. Okay. I will just do one of these exercises as well. I'm going to pick the Eiffel Tower. So I can change this text to whatever I want. And again, the schema extractor, schema from text extractor will take that text, run it through the LLM, and generate me a schema based on that information. As we kind of saw with this. Oops. Oh, there we go. Just as I think, well, maybe this is taking a little bit longer, it returns, right? So we have a node type of tower, another node type of location. We have some patterns. So the tower has a relationship located in a location. Yeah, so we can kind of see that how we can turn text into a graph schema. All right. So we are going to move on to next question. So we've just been experimenting, just looking at how we can turn text into a graph schema. But what we are going to do now is we're going to go through the process of creating a graph from unstructured data. So there is a class within the Neo4j GraphRAG package called Simple KG Pipeline, Simple Knowledge Graph Pipeline. I really wish we hadn't called it simple, because simple suggests you can only use it for simple things. That's not true. The simple comes from it's got a very simple API, right? And it's a great way to get started. So the Simple KG pipeline is a pipeline which implements those series of steps that I described. So it loads text, splits into chunks, creates embeddings for each chunk, extracts entities, and then writes the data to a Neo4j database. So it does all of those things in one step. And then broadly, the pipeline looks like this. There's a loader, a splitter, a chunk embedder, entity and relationship extractor, a pruner, take out stuff that's maybe duplicates, things like that, a writer, and then there's also this idea of a entity resolver. So if you've got a very complicated knowledge graph, two entities that may be similar but described differently. So you can do entity resolving as well. So this is what you are going to do. You are going to create a knowledge graph from text within a Graph Academy course. So it's actually the Neo4j and Generative AI Fundamentals course, but it's a course that describes GenAI, RAG, GraphRAG. So what we're going to do is we're going to build a knowledge graph based on that information, and then we'll build some retrievers that allow us to ask questions about generative AI. So it's going to take this text, it's going to take this PDF document, run it through this pipeline, and create this graph. So you have a task to do. Your task now is to, in the same way, we're going to start by opening some starter code. We're going to review it. We're going to run the pipeline to create a graph from a PDF document, and then we're going to have a look at the graph and the entities extracted from the text. So, slide says continue with the lesson to review. So if we look down here, here is all of the information for you, so you can go through, complete this activity. I will do the same as well, but I will just take a breath just to kind of look if there's if there has been any questions as well. All right, so we are here. Your task is to open up this file, so workshop GenAI KG builder. So if we go back to our code space, here is the file KG builder, and here is the code. So yeah, first job, review the code and run it, and then review the results as well. Let's just have a quick look, see if we had any questions. Everyone records. Thank you for sorry, this is from Akmal. Thank you, Akmal, for responding. Okay, cool. Again, if you have questions, put them in the text. There are points throughout this workshop where I will go through. Siva, can you explain the code yeah, I'm going to do that now. That's the thing I'm going to do now. Yeah, so there's if you're working through the content, please do. There's explanations in terms of what the code does, but again, I will go through the process as well. So this is this program. This is this KG builder. So we've got some imports. It's going to use that GraphRAG package. So the first thing we need is a connection to our database, and that's what this does. This creates a Neo4j driver and verifies that we can connect to the database. We need an LLM. That's how we're going to do our entity extraction. So we need an LLM. In this case, I'm using GPT-5 Nano. We need an embedder. So we need a way of turning text into vectors. We're using OpenAI embeddings. I happen to be using this text embedding model, Ada 2. We then configure our knowledge graph pipeline. So this is the pipeline that does those 5 steps, right? Load, chunk, embed, extract, write. Tell it what LLM we're going to use. Tell it what connection to our database we use. Going to tell it what embedder to use. In this case, we're setting a flag to say the documents are PDF documents, and then finally we run it. So we're going to load in our PDF file. So it's coming from Workshop GenAI data. So if we go in here, these are all of the PDF documents from that course that we are going to use as the source for our application. And if I just look at one, we can just see that it's it's text that describes generative AI models. It all look pretty familiar to you. It's essentially the slides that we went through earlier. And I have lost the program. It was this one, wasn't it? KG Builder. So we load the PDF document and then we run the KG Builder pipeline. We run the Knowledge Graph Builder pipeline, passing into it that PDF file. So we can just run it. Let's run it. And what it's going to do is it's going to load that PDF document. It's going to push it through that entity extraction model, and it's going to generate our knowledge graph. Siva asks, what is an embedder? We will talk about embedders, but in summary, an embedder turns text into vectors. So it turns text into numbers that allow us to query it. Yeah. Okay, cool. So it has done a thing. So my program has run, and so essentially it creates a structure that looks a little bit like this, which is there is a document, the document being the PDF thing. For each document, there will be one or many chunks, and then there will be entities that have been extracted from those chunks. And we can look at those, right? So once we've run the program, we can look at it. So if I run this query, we can see that, yeah, lo and behold, there is one document, which is that PDF document I just ran, and it's got the text in it from that PDF document. Now, at the moment, the chunk size, so that is actually greater than the length of this document. So we're only getting one chunk created, but that's fine. One of the things we'll do next is look to modify the chunk size. And what we should be able to do is have a look at the entities that have been extracted from that. In fact, no, we can't. Why can't we do that? Okay. I think there's a problem with my query. There is a problem with my query. What's wrong with my query? Feels like something I need to fix, doesn't it? But yeah, so what I've done is I've just written a very simple query that matches all of the entities that were returned, and we can see that there were two of them. So the two entities that were returned was LLMs and generative AI. So we can see that the two entities extracted from that piece of text were LLMs and generative AI. So it's gone through that process and it's created this graph, albeit not a very exciting graph, right? What we are going to do is we're going to spend some time changing this program to define a schema, so to define the information that we want, and to kind of run it multiple times to improve the graph that we get out. But we've proven that by running that process that we have created a graph, albeit a pretty simple graph, that basically says, in this document, there is an entity which is a model of LLM, and in this there is an entity of generative AI in this document as well. All right. Again, be super helpful. Like, have people managed to run things? Nice to hear. Little thumbs up, something like that.
Martin, this is Akmal. Just a quick question. The OpenAI API key that's in the docs, that's good to use for today, isn't it?
Yes. So the OpenAI key that's in the notes document, this one here. Yeah. That is good to use for today. After this session, I will revoke it. Yeah. But yeah, for while we're talking, yeah, you can use that.
Great. Thank you.
Okay. Okay. Hopefully some people have managed to kind of run the process and kind of like run the knowledge graph builder. What I'm going to do is I am going to before we move on, I will just do some questions, but like I said, I would do. Can we use other LLM like Gemini? Yes, you can use whatever LLM you feel is right. I'm using OpenAI for no other reason that I have access to it, right? You know, yeah. And other models will deliver different results, right? Pick a model that kind of fits your use case. OpenAI's model tend to be consistent, good for general purpose. Yeah. Okay. All right. Let's move on to. So we have gone through the process. We've taken our document and we have created a graph from it. What we're going to do now is we are going to look to change the chunk size, right? And chunk size is important. So the graph that was created has essentially only got one chunk in it, right? By default, the chunk size is quite large, right? Now, the larger the chunk size, the more context the LLM has when extracting entities and relationships, but it also may lead to less granular data, right? So what we're going to do is we're going to modify the chunk size, yeah, but chunk size also has an impact in terms of the data that's extracted and the sort of specificality of it. So chunk size is one of the chunk size and chunking strategy is one of those things that it's worth spending a little bit of time on, sort of based on your data. So your task is to modify the chunk size. What you're going to have to do is delete that existing graph, create a custom fixed size splitter, modify that pipeline to use it, and run the pipeline. And then we can look and see actually, well, what was the changes as a result of that. Siva, you asked a question. So before we do that, I'll just kind of move on. Siva, you asked the question, where do I see the knowledge graph generated by KG Builder? So if you go back to Graph Academy, at the end of the course, at the end of the lesson where you create the graph, there's some cipher statements that you can run. You can actually run them in Graph Academy. And when you run this cipher query, it runs it against your Neo4j database. All right, but yeah, we are on this lesson here. We are on chunk size. and your task is to modify the chunk size. Carl asked a question, what about locally available LLMs? Yeah, fine. That's fine as well. Whatever LLM fulfills your requirements. The GraphRAG for Python package that we're using has adapters built for lots of the like the normal ones, the big ones, right? Including Ollama. So if you're running a model through Ollama, that's fine as well. But you can create your own interface as well. So if you wanted to use the simple KG builder, you can create your own interface to talk to any LLM you want. Yep. Raj, yeah, it depends on what locally available LLM you want, but yeah. All right. So this is your task, is to modify that chunk size. What I'm going to do is I'm going to do the same thing as well. Right. So I'm going to go through the process. So we're going to be re-importing the data. So I'm actually going to delete everything, right? So if I run this in Graph Academy, it actually deletes everything in the graph. And I'm going to go through the process of modifying the chunk size. So so we're back in our KG builder program. I need to import the KG builder and I need to create a text splitter. So I've imported it, create a text splitter, and I basically set up a chunk size. So this is how big I want each chunk to be, and a chunk overlap. So the overlap being we'll have 100 characters of the previous chunk in the next chunk. That's really useful if you to make sure you don't miss information. So modify my chunk size, and then I can update the KG pipeline to use it. So right at the end, we're going to modify the text splitter. So we're going to add additional parameter to our KG builder to use the text splitter that we just created. And then I'm just going to run it again. I'm going to go through the same process. So again, it's going to go through exactly the same process, but the change here being that it's going to split the data into smaller chunks. And the interesting thing that we can see is that actually we got more data out. So if I now look at the graph that has been created, so first of all, let's have a look. So if I run this, I can now see that there are, for the one document I've got, there are now multiple chunks. Yeah. And if I look at the entity relationship graph, we can see that there are more entities that have been extracted from those chunks. And actually, if I just do match entity and just return them all, we can see these are all of the entities that have been extracted from that data. So there's training data. So training data, LLM prompts trained on training data, and we can see which chunk it's from. So the training data entity came from this, the probabilistic continuation of the training data. So we've got text to image, but yeah, we can start to see the entities that have been created from just that simple piece of information. So anyway, start to see our graph being created. I'm just going to give you a moment to do that. Akmal is doing an incredible job answering questions because I don't have any running any to do. Yeah, Akmal, yeah, I'd agree with what Akmal has said. Lots of talk about using local LLMs. Yes, pick a model that suits your use case. And always my advice is test and experiment. The models are different and they deliver different results. Okay, but what we can see, so the graph that we have created has now got considerably more entities in it. Yeah, by chunking the data, by making it smaller, we have created something that is more specific. Yeah. So again, chunking strategy is really important. Now, my strategy has been really simple, which is essentially just number of fixed characters. how you chunk your document is entirely up to you. You know, it doesn't have to be on sizes. It could be on sections. It could be on some other meaning. It could be making them bigger. You know, putting additional metadata data in them doesn't matter, right? But it's worth exploring your chunking strategy. All right, so we've got our graph, we've taken our data, we've chunked it up. What I want to look at now is defining a schema. All right, so the knowledge graph that you created is unconstrained, right? So it basically means that any entity or any relationship that can be created based on the data could be. Now this leads to graphs that are non-specific, and actually when we looked at the graph that had been created from that data, there was all sorts of things in there, right? It wasn't noticeably helpful, right? So what we are going to do in this lesson is we're going to look to modify that pipeline to create a custom schema. So if we provide a schema to our knowledge graph creation, right, it instructs the LLM to only identify specified nodes and relationships. So we can define the schema with whatever we want, and typically we do that in three ways. We define nodes, so the sorts of things we are looking for, you know, people, organizations, locations. The relationships, so how those the relationships that we are looking for between entities. And then the patterns, so the patterns being how the entities, the things, are related to each other. Now we can describe all three of those things, one of those things, or two of those things in any order. So we can kind of mix and match how we look to describe the schema that we are looking to get out. But it's always those three things: nodes, relationships, patterns. Okay, so again, your task today is to open up the starter code, which is this KG builder schema, and review the code. What I then want you to do is define a set of nodes, relationships, and patterns that are relevant to the data, and then modify the KG pipeline to use it. Yeah. And then we'll run the pipeline, we'll iterate, and we'll refine it multiple times. And then we can look at the graph. So we'll run it, define a schema, review it, iterate the schema, and then review it again. Okay. So this is your task. Just to kind of recap where we are in knowledge graph construction. We are in the lesson around defining a schema. And again, I'll take a moment to just kind of look over questions, and then I will go through the same process as well. Okay. I'm not okay. So VJ, Neo4j GraphRAG. How are document chunks mapped to graph nodes, and how are semantic relationships between chunks established? So Neo4j doesn't dictate how we chunk things together. In the examples that I have been using, documents are mapped to chunks through a document has chunk relationship. I think it is. So documents, there's a relationship between documents and chunks. Chunks are related to entities, basically through a chunk has entity relationship, and then entities can be related to any other entity within that graph. How are semantic relationships between chunks established? So in the example that we have been doing, they are established by the LLM doing entity and relationship extraction. So the LLM will come up with any entities and any relationships that exist within those chunks. Now, obviously, there are multiple chunks that are being where we're doing entity extraction. So if the same entity is found within two chunks, that single entity is used. There's no duplication. Right? So that's how we establish relationships between multiple chunks that have the same entity related in them. And through that we can define meaning. Yeah. All right. Okay. Raj, I'm not going to get into your question. It feels like more of a discussion. I don't think I'll be adding more than's already been discussed. Okay, great. All right, so I'm going to do the same task. What I'm going to do is I'm going to add the schema to the pipeline. If you've been following this lesson, it goes through adding things like node types and information. What I'm going to do is I'm going to sort of cut to the end, right? So, where are we? I've got slightly lost myself. Okay, here we go. All right. So within the unstructured data that we are using at the moment, is a lesson about generative AI, or it's lessons about generative AI and using Neo4j. So the nodes that I think are important within that text are things like technologies, concepts, examples, processes, challenges, benefits, and also things like resources. So in this case, a learning resource where people could find out more. So what I am going to do is I am going to, first of all, let's go back to my program. Here's my KG builder. I am going to just define the nodes that I am looking for. So here are the node types that I'm looking for: technologies, concepts, examples, processes, and resources. You can see with resources, the way I've defined this node is I've actually given it a lot more information. So I've actually given it a description and some properties that I'm looking to extract as well. You don't have to. If you don't, it assumes a description and it will extract properties such as name, name and ID. But we can be more specific if we want to be. We'll just delete my graph actually when we're here. What I can also do is define relationship types. So the relationships that I think are important within this text are things like related to, part of, used in, leads to, has challenge. Again, this is educational content. These are the things that I think are important within the text that we are extracting. So I've got my nodes. These are the nodes I'm looking for. These are the relationships that I'm interested in, and I'm also going to describe some patterns as well. So the patterns that I'm looking for are which use those nodes and those relationships are. I want to know where technology is related to other technologies. I want to know where concepts are related to technologies, where examples are used in specific technologies, so on and so forth. So I've got my nodes, my relationships, and my patterns. Those are the things that I'm looking for. Those are the things I want to get out of my unstructured data. And then it's just a case of telling the KG builder to use them. So there we go. So find a schema. Here are the node types. Here are the relationship types. And again, let's just run it. So let's give that a run. And again, it's going to go through exactly the same process. It's going to chunk the data. It's going to do that entity and relationship extraction. But specifically, what it's going to do now is it's going to look for those very specific entities and relationships. All right. So the process has run. And interestingly, what we can see is this was the first time I ran it with just one chunk on a large document. I got two entities to resolve out. I ran it again, I get 18. I ran it again, I got 25. So what we're seeing is the more specific we are about the information that we are looking for, the more useful data that we get out. Okay. So let's just have a quick look at explore that graph. All right. So let's have a quick look and explore this knowledge graph. So what we get out now is there is a technology called a technology node related to prompt, which is related to another technology, LLM. What have we got here? We've got generative AI. The technology is related to technology, large language models, code generation, image synthesis, content creation, chatbots. Oh, and then we have our chunks as well. So this entity is part of this chunk. It is also part of that chunk. Yeah, so we can see how generative AI is related to multiple chunks. Yeah. We can see that there is an example of a prompt which is used in a model. And we've also got intent, which is related to model. And what's this final one? A process. Ensures that the model understands, is part of this technology, and is from this chunk. So we can starting to see how our knowledge graph is being built up. And again, our knowledge graph that we're creating so far, remember, is on one small document that describes, what is generative AI. Yeah, so we can also do things like run this query here. So we've got one document, 9 chunks, 23 entities found. Yeah. Okay. So again, I'll just give people a moment just to kind of go through that content, and we'll look at any questions. Okay. So Siva, what's the use of chunking? Akmal, thank you for coming back. Yeah, it's essentially, as Akmal says, it's breaking down that information. The one thing I would say is large chunk. If you pass large chunks to do entity relationship extraction, what you tend to get back is only the very high level information. That might be what you want, but the smaller the chunk, the more specific the entity relationship tends to be. Simran, but isn't storing full information only making a relationship? I'm really sorry, sir. I'm not sure what you are referring to. If you can provide a bit more context, maybe I can come back to you. Does Neo4j GraphRAG avoid that more context equals more hallucination, often seen in vector RAG? Yeah, I mean, so VJ, you come across a really important point, which is if you are only using vector-based RAG, and we will see examples of this, what you end up with is very big context windows, because essentially your vector only takes you to a chunk of text, and that chunk of text could be quite significant. And if we pass all of that text to our LLM, the more context it has, the more likely it is to hallucinate. What GraphRAG allows us to do is to supplement that information, or to replace that information with facts from a knowledge graph. So much less context. Yeah, less context, less hallucination, I would say. Yeah. The absolute opposite of what you've said. More context equals more hallucination. Yeah, put it the other way around. GraphRAG typically provides less context. Yeah. Okay. All right. So where are we? Yeah, we're okay. What we're going to do now is we are going to add some structured data to our graph. So at the moment, the graph that's been created is solely based on that unstructured data, right? But if you have structured data about your unstructured data, you should put those two things together, right? And that structured data could be, metadata. It could just be, information about your domain, because combining that structured and unstructured data can enhance our knowledge graph's richness. All right. So the repository contains some structured data. I mean, it's in the form of a CSV document. So if we just have a look at it, there's this docs.csv document. Now, it's not particularly exciting structured data, but it's information about the files. So there's the PDF file, and we've got what course it came from, what module it came from, what lesson it came from, and what URL it came from. Right. So we can provide some structured data along our unstructured data. So that's what we're going to do. Right. We are going to create a graph that looks like this. So at the moment, we've got documents, we've got chunks, and we've got entities. The entities are what have been extracted from the chunks. What we're going to do is we're going to create a new node which represents our structured data. That will have in it the name of the lesson, the module, the course, and its URL, where to go in order to be able to do that. So we're going to go through a process of adding structured data. Okay. So your task is to open up that KG structure builder file. We're going to review the code and look at how it uses Cypher. So Cypher is the Neo4j query language to create nodes from that structured data. And then we're going to run it. Then we'll review the graph and how the structured data gives us new ways of exploring that information. So again, continue with the lesson. Continue with the lesson, wherever it is. Continue with the lesson to load that CSV file. add the additional information, and then ultimately what we're going to do is we're going to run it for the whole thing. We're going to run it for all of the lessons and all of the documents to create one big graph. All right. Oh, what have I done? I've managed to go back. Okay, there we go. Right. So again, this is your task. Again, I'll look at some questions, and then I'll come back and I'll go through the same process as well. What do you prefer? Do we use multiple PDF-based data for breaking down chunks, or do we use pre-built databases? Which of them reduces hallucinations? I mean, what I would say is if you have structured data, you should always use it, right? If, however, you have data that is hidden in documents, then supplement your structured data with it, right? Unfortunately, what we find is that a lot of the data that's useful for our generative AI applications tends to be unstructured data. But if you've got structured, well-verified data, you should definitely use it. Okay, I will keep an eye on the questions, and I'll kind of go through the exercise as well. All right, so let's just have a bit of a tidy up, because I've got code going everywhere anyway. So this is the structured builder program. So it looks pretty similar to what we've run before. We've got our connection, we've got our GPT LLM, we've got our embedder, we've got all our schema information that we just added. But what we've also got is we have got code that opens up that CSV file. And we've also got a cipher statement as well. So what the cipher statement does is it says, okay, we'll find the document that has been created. Merge creates a node. It basically creates a pattern in the graph. In this case, it's a node with a lesson label. And it's going to set some properties against that node. And then it's going to create a relationship, a PDF of relationship between the document and the lesson. So the document is a PDF of that lesson. So this is the cipher statement that's going to insert the structured data into our graph. So this is going to go through every document in that CSV file. So these are all of the PDF documents that are in here. Going to go through every document in that CSV file. It's going to run it. It's going to run the entity extraction that we have been using, and then once it's done the entity extraction for each document, it is going to create that structured data. It's going to create that lesson node by executing that cipher statement that we just looked at. All right. So this is going to go through all of these documents, do entity and relationship extraction for that schema, and add that structured data as well. So I'm going to run it. It's going to take a little while to run. But yeah, it'll take sort of a minute or so, and this will give us give me a chance to have a breather and also kind of look at some questions. Oh, the thing that I forgot to do, which I should have done, was I want to start afresh. I want this to be brand new. So the thing I'm going to do is I'm going to delete all of the data. Okay, right. I was having some sort of error, but yeah, I've deleted all the data in my graph. I'm just going to run it again, just because I want it to be fresh. I don't want to be. I don't want to have old test data in there from the previous runs that we just did. Okay, so it's going to go through and do that process. Okay, like I say, it'll take a minute or two to run. To go through every document. Most of that runtime, interestingly, is going to the LLM to do the entity and relationship extraction. So, where are we? How do you handle conflicts or evolving relationships in dynamic knowledge graphs, especially when the underlying source documents contain contradictory information? For example, on FIFA database. FIFA? Do you mean you mean like football? I don't quite get the reference about FIFA, but that's fine. And in terms of your question, I think as Akmal says, deleting relationships that no longer exist is the right approach, right? We should look after our graph, our knowledge graph, in the same way we would do any domain information. I think one of the things that many people don't realize, and when they first start using Neo4j's, Neo4j is a full ACID compliant transactional database. You can delete things, move things, change things, it's all fine, right? Oh yes, football. I did, for example, on FIFA database, conflicts in dynamic relationships. Yeah, I mean, you're right. Oh, okay. Things change, right? Things change in football. I think I get your reference. I get your meaning. Yeah. Okay. Okay. So still running. I think I'm nearly there. I think I've got 4 documents left to do, and I've now got 3 documents left to do. But what we should be able to see is, even with having not completed task yet, we should be able to explore that structured data as well. So we've added structured data to the graph. We now have, we now have lessons, right? So if I, match all the lesson nodes and return them, I'm going to get back a collection of lesson nodes. So for this particular lesson, we've got information in it, such as the URL. And I can click on it, open the URL. Yeah. What course it was from. So we've got our structured data within our lesson node, and we can see that lesson node is a PDF. There is a PDF that represents that lesson node, and then that PDF has lots of chunks. Each one of those chunks will have entities associated to it, and those entities will have relationships to other entities. So we can see how our graph has started to build. Now we can use that structured and unstructured data, right, to find information. So if we match all of the technology nodes within our graph, right, we can then use the technology entities to go through the chunks. So if we go from the knowledge graph to the chunk to the document to find the lesson, right? So we can ultimately find any lesson which references knowledge graphs. And there we go, right? So the knowledge graph extraction, knowledge graphs. So we can see the lessons where the technology knowledge graph is used, and the link to each one of those lessons. That's right. So we have used our unstructured data to find us access to our structured data, because ultimately if we're saying, right, find me information about knowledge graphs, we can go direct to those lessons as well now. So the knowledge graph allows us to summarize content as well. So this says match all the lessons, find the chunks for each one of the lessons, and then from the chunks find the technologies and the concepts that are referenced in each one of those lessons. So what is generative AI? It has got the following technologies and the following concepts. So again, we can use our knowledge graph to summarize the data or the information that's within our unstructured data. I'm trying to find, so considerations, references, technology, LLMs, and the concept of hallucination. Again, the same lesson references, or a different chunk within the same references temperature. So the technology temperature and the concept of randomness. Yeah. So we can see how we can take our unstructured data, turn it into a knowledge graph to allow us to be able to summarize it in ways that we couldn't necessarily do before. Okay. All right. So we have a knowledge graph. We've done well. We have a knowledge graph that we have created from unstructured data. It contains structured data about our lessons, it contains the text from our PDF documents that has been split into chunks, and then for each one of those chunks, we have extracted technologies, concepts, benefits. I can't remember what the other ones were, resources, right, about those those chunks. Sorry, I don't know. And we can query that graph, and we can query that graph as well. So let's go up and find all of the benefit. Well, there's only one. Okay. Enhance information retrieval is a benefit. Lesson summary leads to advanced information. GraphRAG leads to GraphRAG. The technology leads to, oh, this is beautifully put, the benefit of enhanced information retrieval, which comes from this chunk being there will be a document somewhere from document. This document relates to this lesson from this course with this URL. So yeah, we can move things. We can now move through our knowledge graph and understand our data in a way that we couldn't when it was just a handful of PDF documents. All right. Okay. I would encourage you. This content is yours now forever. If you want to create your own knowledge graph, there's some information here on how to do that, and it's also got some open data sets for you to try as well. But what we are going to do in the last section of this workshop is we're going to move on to this third module, which is about retrieval. So we are going to use our knowledge graph to do vector RAG, vector plus cipher and to create a vector plus cipher, a GraphRAG retriever, and also to do text to cipher retrieval as well. So what we're going to do now is we've created our knowledge graph from our unstructured data. We're now going to use it to retrieve data and use that as context for an LLM to provide information and responses to us. All right. So just to kind of recap, we're on this last module here, which is retrieval. Yeah, this is what we're going to do. All right. So let's just do a sort of 5-minute reflect on what we mean by vector-based RAG. Again, let's just make sure we all understand the terms we're going to use. Right. So we heard right at the start about RAG, about retrieval augmented generation, and the role of retrievers. So the retriever's role is to find information, relevant information about the request in order to provide context to the LLM, right? Now, we are going to look at semantic search and how vector indexes can help us do that. And then we're going to build on that to look at how we can use graph retrieval to enhance that vector search as well. All right. So when I talk about semantic search, what I mean is search that looks to find intent and meaning, yeah, not just focusing on individual keywords. So if you were to search for apple, right, you might predominantly get results about fruit, right? However, in semantic search, the engine tries to gauge the context, right? So are you searching about fruit, the tech company, or something else? So the results of a semantic search are tailored based on the term and the perceived intent. What are you trying to do, right? And the fundamental technology that supports semantic search is vectors, right? So again, vectors are a list of numbers. And we can use vectors to represent different types of data. So if we had a point in 3-dimensional space, we could represent that with a vector of 3 numbers. So, X, Y, and Z, right? The number of numbers, like the number of dimensions in a vector is called its dimensionality. Yeah, so 3 numbers, we can represent a point in 3D space. So, and typically, the more dimensions you have, the more fine-grained meaning you can gain from that. All right. So, somebody asked me the question, what is an embedding, right? So, semantic search rely on vectors to work. When we talk about embeddings, right, the term embedding is typically used within like machine learning and NLP, generative AI, when we want to represent a particular semantic aspect, right? So an embedding is a vector, right? An embedding is just a list of numbers. We tend to use the word embedding when we have created a vector for a specific purpose, right? So we may create embeddings, yeah, to support semantic search, right? When we create an embedding, for say for the word apple that we've just been talking about, they would have lots and lots and lots of different numbers, lots of different dimensions. So there might be a dimension for fruit, technology, color, taste, shape, whatever. And we can compare vectors together. So we can compare the word apple to the word technology, right? So the way you create embeddings is through an embedding model. So the activities that we have been doing today, when using that simple KG pipeline, we provided it with an embedding model. And what the embedding model did for us was turned a chunk of the text into a list of numbers. Right. So typically, we don't create embeddings for single numbers. We tend to create embeddings for sentences, paragraphs, whole documents, right? The bigger the larger the piece of text, the more meaning it will have, right? But the less specificality. It's down to the same chunking decisions as well. All right. So we can compare vectors together, and that is how we can use vectors in semantic search, right? If we are searching for the word apple and we want to see how similar it is to the word fruit, if we have a vector for apple and a vector for fruit, if we measure the distance between those two sets of numbers, we can understand how similar those two things are. All right. So the way semantic searching works in vector-based RAG is typically what you do is you take your source data, you push it through an embedding model, you create an embedding, a list of numbers, and you put that embedding in a vector index. The vector index allows us to search the embeddings very quickly. So going back to our RAG-based question, right? How does RAG work? User provides a question, a prompt, right? The application takes that question, creates an embedding for the question, searches a vector index using the question as the search term, gets the results back, and uses those results as context for the LLM. Traditional vector-based RAG. All right, so what we are going to do now is we are going to create a vector retriever. All right. So just to kind of recap where we are here. I'll get to questions in a moment because there's going to be a pause where opportunity for you to do things. So we are on this second lesson here, vector plus cipher retriever. Okay. So the chunks in the knowledge graph include vector embeddings, right? So when the KG pipeline created those chunks, it also embedded them. Let's have I'll show you. Match C chunk return C limit 10. So I'm just returning the first 10 chunks. So these are the chunk nodes. If I select one of these chunks, we can see the properties against that chunk are the text, but also an embedding, a list of numbers. So yeah, there are embeddings for those chunks. What we're going to do in this lesson, we are going to create a vector retriever, yeah, that finds that uses those embeddings to find the most relevant chunks for a query. And then what we're going to do is we're going to add on to that vector search the ability to look at the graph and use GraphRAG to use the information in the graph to supplement that context. All right. So in order to use those embeddings, we need to create a vector index. And this is the way we do that in Neo4j. Create a vector index on chunk nodes on that property, which is where the embedding is installed, and we give it some options. So the options being how many dimensions are in that vector, and also what similarity search do we want to use. In this case, we're going to use cosine. But yeah, if I run that, it runs, and we have a vector index. That's it. It's not particularly difficult. And And we can search that vector index by creating an embedding for a search term. All right. So let's just have a quick look at this query. This says, use this function to create an embedding using this model of the phrase retrieval augmented generation. And then what we're going to do is we're going to search the chunks using that embedding. So we're going to search that vector index using the embedding that we created for retrieval augmented generation, and then we're going to output the chunks that we find and the score. All right. So I'm going to run this. Now, in order to run this, I need to provide that OpenAI API key token. So I'm just going to take it out of here, and pop it in there. All right. So run this query. We create an embedding for retrieval augmented generation. We run this search, and we should get back chunks that are equivalent to retrieval augmented generation. All right. And we have, right, the first one we get back is what is RAG? That's handy. So we get back a series of chunks. So in fact, we should get 5 back. We get 5 back because that's how many I asked for. And if we look, we also get a score. And essentially what it says is the embedding for retrieval augmented generation is 0.93, right? 1 being exactly the same, yeah, lowering down to 0 being further apart. So 0.93 being pretty similar. So we can use Neo4j to search for vector indexes, to find semantically similar information. Now, what you are going to do is you are going to build a retriever in Python. You're going to use that vector index to search the data, perform a similarity search, and then you're going to update the retrieval query to add additional information from the graph based on the information that you get back. Okay. Right. So this is a good time for me to pause. I will do the activity as well, but I'm just going to go have a quick look at any questions as well. But yeah, your job. Open this file. So your GenAI workshop vector cipher RAG. Review how it works. Like I say, all the instructions are in front of you. Again, if you've sort of lost where we are, we're on this 3rd module retrieval, and we're in vector plus cipher retrieval. All right. Okay. Oh, we've only had one question. Akmal, not yeah. Akmal. So Akmal says, I think GraphRAG will not completely replace vector RAG. We use the technology that fulfills our use case, right? GraphRAG provides a significant improvement to vector-based only RAG for lots of use cases, and yeah, it's often called hybrid retrieval as well. All right. That's our only question. So I think I'm going to I'll carry on and do the activity as well, and I'll kind of talk you through the code. All right. So we're going to open up this vector cipher RAG program. So it's this one here, vector cipher RAG. And if we have a look at this code, we can see things that make sense to us that we've seen before. We still have our connection to our database. We are still going to create an embedder because we need an embedder in order to be able to turn our query, our question, into an embedding so we can compare it against the vector index. We define a retrieval query. So this is the information that we are going to get back. This is the information that we are going to get back. And so we create our vector cipher retriever. So this is our retriever. It's got a connection to our database. Tells it the index we're going to use, the vector index we're going to use, what embedder we're going to use, and what retrieval query. We create our LLM. We create our GraphRAG pipeline. So what our GraphRAG pipeline does is it pairs up a retriever to an LLM. Yeah. And we give it a query. So what is a knowledge graph and where can I learn about them? So this is our query. We pass this to our GraphRAG pipeline and we get a response back. Give it a run, see what happens. So what the retriever is doing is it's creating an embedding of this question. It's used that vector index to gather some context from the knowledge graph and has then passed that context to the LLM to generate a response. And the LLM comes back a response. A knowledge graph is organized representation of real world entities, people, places, and things. You can read on. You can learn more in the blog post, what is a knowledge graph. All right. So we can use our vector index. We have done RAG. We have done vector-based RAG. So here we go. This is where we are. All right. Actually, let's just have a quick look. So one of the things we can also do is, at the moment, I'm just printing out the response. What I can also print out is the context that it used. So I can actually have a look and say, okay, well, what context did you use in order to be able to generate this response? Again, it runs pretty quickly, but what we see is we see this context block here. So we can see that we have text that is made up of the that's retrieved from the chunks within our knowledge graph. It's not that easy to read, but we can say, you know, there is definitely a chunk here that represents the that has strongly influenced the response that we've got back from the LLM. I'm just going to take that out. It tends to get a little bit confusing. All right. Okay, so that's good. We have a vector-based RAG system. The other thing I can do is by modifying that retrieval query, I can change the data that comes back. So in this case, I'm going to change the data. I'm going to change the query so it returns information not only from the chunks that we get from our semantic search, but also from the knowledge graph itself. And we saw this query earlier. This is the one that finds related technologies and related concepts. All right. So let's just give this a run. So let's copy our retrieval query. So I'm going to go back to my program and I'm going to modify the retrieval query. So rather than just getting out some text, what I want to do is I want to use our knowledge graph to get more information. So data I'm going to return now is the text, as we had before, the score, a URL to the lesson, but also any related technologies and concepts. Let's give that a run. I'm going to ask exactly the same question. What is a knowledge graph and where can I learn about them? So I run that and I'm going to get a response based on the context that I passed in, the context being what I got from my knowledge graph. So a knowledge graph is an organization representation. So that's good. That's good information. That's based on the context that it was given. But interestingly, I get more information out now. You can learn more here. So you can learn more in the Graph Academy lesson or this blog post. If I looked at what I got out previously, the only information I got out was about the blog post. So I've been able to supplement the response that I got from the LLM based on the information stored within my knowledge graph. The other thing that I can do is I can do things like generalize entity retrieval. So the retriever uses that knowledge graph to add additional context. If I look at this cipher query, so what this does is it finds all the chunks and it finds all the entities, finds how they relate to each other. Hang on, let me just tidy up because I've got all sorts of things running. Let's make this a bit bigger. So this query here uses the knowledge graph to find how things like how the entities in the graph are related to each other. So the concept of patterns is related to the technology of, I need to make things a bit bigger, probabilistic continuation of the instruction it receives, right? The concept of the process of prompts is part of the technology. We can see the idea how we can use the information within our knowledge graph. So the concept of an LLM is related to the technology of prompt, right? So we can see how we can use the knowledge graph to define facts or information. Okay, so the sources for this training data cites the technology access to data. So we can see how we can use the knowledge graph to define facts and information. And we can create more sophisticated retrieval queries. So this retrieval query, again, matches, returns the lesson text and the URL, but it also uses the knowledge graph to define these facts and information, like technology retrieval augmented generation has the challenge of understanding what the user is asking it to find out. So again, we can create much more sophisticated retrieval queries. I'm just trying to find my retrieval query, which is here. And again, if we run with the same question, we get we get more sophisticated responses. Oh, here we go. Now something's definitely changed, but I'm not sure what it is. Peace ban the relationships between the countries and entities, and this structure must be. Okay, it's this bit that's changed. Yeah. Again, so the way that we use our graph to supplement the information is up to us, right? And again, there are some examples that you can try. Okay, so the last thing I'm going to just move on to is how we can use text decipher. So we've learned about how we can use how we can build a knowledge graph and how we can use that knowledge graph through vector-based RAG and just through cipher queries to find information about our text. But what we can also do is use text decipher. So text decipher allows us to create pipelines which turn natural language into cipher queries that we can query our graph using. All right. So again, you've got a task to do. So your task is to create a text decipher retriever, GraphRAG pipeline. I'm sure you've understand the pattern of how this workshop works. There is some code for you to open, review, run, change, see how the results change. All right. Okay. Let's have a quick look at sort of questions. So VJ and Akmal seem to be having a question. Neo4j is the leader in graph databases, but other tools like TideGraph and Amazon Neptune are also growing. What makes Neo4j better for GraphRAG and enterprise AI applications? I mean, VJ, I think you've said the word yourself. It is the leader in graph databases. Neo4j has the biggest ecosystem. It is the most established. It has the highest, particularly for enterprise, the biggest opportunity to scale, so on and so forth. I'm not going to do the sales pitch on you. In terms of you have to follow up question about good documentation, workshop, hands-on courses. Go to Graph Academy that I have been using. You will find huge numbers of courses on things like GraphRAG. There is a whole GenAI knowledge graph course and learning path for you to follow. Okay. Actually, I'm working in GCP-based enterprise environment. Can you share any good documentation? Yeah, so definitely use Neo4j. But yeah, as Akmal says, you can use Neo4j on your cloud provider of choice. Yeah. Or you can use ours, Neo4j Aura. Okay, so again, I'm just going to go through the activity to create and look at this text decipher text decipher retriever. Thanks for the hands up. If you have questions, stick them in the comments. Oh, I think you just pressed the wrong button. That's fine. All right. So let's have a look at this text decipher retriever. So here it is. Again, let's just do a bit of tidying up. Here's my text decipher retriever. And again, I'm sure these things are going to start to look familiar to you. So we still need a connection to a database. We still need an LLM. And actually, what our LLM is going to do is it's going to do two things for us. It's going to act as the agent between me asking a question and getting a response. And what it's also going to do is it's going to turn our natural language question into a cipher statement that we can run against that graph. All right. So one of the things that works really well for text decipher is if we provide it with examples. So I've included a simple example here. Find a node with a name. So if you need to find a node, yeah, you can use this query, and it basically says use case insensitive search, right? But we can provide as many examples as we think are needed. We build our retriever. Retriever needs a connection to the database. It needs an LLM, and we can give it examples if we wanted to. We give it we create our GraphRAG pipeline. So in this case, we have a retriever and we have an LLM. We have a query. How many technologies are mentioned in the knowledge graph? So when we run this, in fact, I will run it. It's probably no doubt it will return quickly. What Text Decipher does is it takes our query, it takes the schema of our database, it turns the query. It turns the natural language question into a cipher query, runs the cipher query against the knowledge graph, uses that as context to the LLM. I have seen it's just finished running, so let's just go back. Right. So the question I asked was, how many technologies are mentioned in the knowledge graph? 128 technologies are mentioned in the knowledge graph, and it's got that by saying match technology, return a distinct count, and it is then used that as context to the LLM to provide a response. So we can see how we can use natural language and how we can use cipher to query our graph. And Text Decipher is incredibly useful when we're looking for specific results. So numbers of aggregated data, times when, things like that. Things that actually are very difficult to pull out of text are surprisingly easy to pull out of a knowledge graph. This is while this response, 128 technologies are mentioned in the knowledge graph. How many technologies are mentioned in the knowledge graph? That is not a question you could have answered with vector search. If I just used vector search, we would have created a semantic search against our embeddings, returned the top 6 documents, and got back, I don't know, 15 technologies. It's not a question that could be answered unless we had created a knowledge graph to do that. And there's a kind of response here. There's some example questions. So how does Neo4j relate to other technologies? So again, let's just experiment for a moment. Pop that in there. Give that a run. And what it's going to do is, again, it's going to go through the same process. There we go. So Neo4j exception, missing request parameter, expected name. So one of the beauties of doing these sorts of workshops, particularly when we're using LLMs, is that they are not deterministic. They can produce invalid cipher, which we have seen here, which is slightly annoying. Let's try a different example. What it's done is it's taken my example too literally, and the query that it has created, it will be in here somewhere, basically includes the parameter name. So I gave it an example that said find a node with name hashtag. That's a cipher parameter, but LLMs not being perfect, it hasn't replaced that with the name of the technology that it's looking for. And that's where agents, which is where the final kind of module in this workshop goes to, can help us, because we can. There we go. Run the same thing. Okay. So I asked the question: what entities exist in the knowledge graph? The knowledge graph contains the following entities. Blah 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 blah. Yeah. Okay. But that's how we can turn natural language into questions. Well, what resource URLs are referenced? Why not? Let's have a. We have got a minute before we need to finish. Let's just try that request as well. No resource. Okay, there you go. There aren't any. That is a valid cipher statement, but for whatever reason, there are no resources referenced. Okay. All right. So this is where I'm going to kind of draw the workshop to a close. There's a couple of sort of final things I need to say, but there is a final sort of bonus module in this workshop. It's around agents, and basically what takes you through the process of creating a LangChain agent that interacts with your knowledge graph, that allows you to integrate multiple retrievers into your questions. Yeah. If you're interested and you want to know more, please go and complete that module. Okay. Let me go back to my slides, which I have lost. Okay. All right. We're just 5 minutes before time, so I'm just going to spend a little bit of time. Please, if you want to know more about Neo4j, please go to Graph Academy. you hopefully you've been using it, or certainly some of you have. I know you have, because I've seen you have been using Graph Academy throughout this workshop. It is completely free. Lots and lots of hands-on courses, lots of created learning paths. We do free certifications. Everything that you find on Graph Academy is for free. Yeah, so please go and do that. The workshop that we've worked through today is essentially an abridged version, a summary of about 3 courses on Graph Academy. So if you want to go into more detail, you find yourself with lots of questions, go to Graph Academy. You'll find much more information there if you want to delve into more detail. And then other than that, I think it's just, we'll do, if there's any questions or anything that we want to talk about. Other than that, I'm just going to say thank you. Thank you for hosting us. Thank you for Akmal for answering all the questions. I'm sure it's been hard on the fingers. But yeah, thank you all. And if there is any last questions, we'll talk about them. Or if there's anything you want to do to close, we're good.
Yeah, that was a really awesome session, and I was just looking at the attendance. It has been stuck at that range, so that's a very good retention. Thank you so much, Martin. Thank you so much, Akmal.